This lecture will focus primarily on how to draw Lewis structures for covalent molecules. And once we get that under our belt, I'm going to talk a bit about what if you have multiple Lewis structures that seem comparable, how do you select the best one? And we'll talk about formal charges a bit, and then what a resonance structure is. Right, so why so much focus on Lewis structures? Remember that the dots in a Lewis structure represent valence electrons, and for a molecule, drawing the Lewis structure is particularly important because it gives us a lot of information that explains the properties of a substance. So number one, it tells us about the shape of the molecule. And that's important for a lot of reasons, but just to give you an example, the shape of a molecule is particularly important for pharmaceuticals. Many of the medicines that have been developed work because of the shape that they are. They fit into an active site in the body and perform some function we need. So shape is very, very important. But in addition to shape, a lot of the properties for a compound are determined by its structure and shape. Before we get started in drawing Lewis structures of molecules, just kind of a reminder about what a driving force is for many, many chemical reactions. And that is that most atoms are most stable with a noble gas-like configuration, which means they have 8 valence electrons. Okay, that is a full outer shell for most elements. And we call that the Octet Rule, okay, the driving force for 8 valence electrons. And there are some common exceptions that are good to know. There are some elements that are perfectly stable with less than 8 valence electrons. Two of the more common ones are boron and beryllium. Boron is stable with only 6 valence electrons, so you will often see compounds like this that are perfectly stable. And beryllium, even more so, is stable with only 4 valence electrons. So you'll see structures like this which are stable. More common than the elements that are stable with less than 8 valence electrons are the elements that can expand their octet and hold more than 8 electrons. And that happens to be all elements that are in the third period of the periodic table or farther down on the periodic table. So periods 3, 4, 5, 6, 7. All the elements in those periods can expand their octet, which means sometimes you'll see compounds with them having 10, 12, 14 valence electrons around them. And the reason they can do that is, if you remember, the D sublevel starts in the third energy level. And so it turns out that when we get to the somewhat larger atoms, the D orbitals are nearby in energy and often at least partially empty, because if an atom's going to take on more electrons, it needs an orbital to put these electrons in. And so these empty D orbitals that are close by in energy provide a place for the extra electrons to go. All right, so here are the steps for drawing a Lewis structure for covalent compounds. It is very tempting for students to kind of shortcut and not have the discipline to go through these steps. Please don't. I've seen way too many mistakes made, maybe not on the easy ones, but when it gets tougher. So if you can kind of force yourself to go through these 5 steps that I'm going to present, you will never make a mistake. All right, so step number 1 is count up the total number of valence electrons in the compound. So phosphorus, and if you haven't already memorized the number of valence electrons for the common elements, you need to do so. Phosphorus is in group 5A, which means it has 5 valence electrons. Chlorine is in group 7A, which means each of the chlorine has 7 valence electrons. So adding those up, we have a total of 26 valence electrons. Now that's important because when we draw our Lewis structure and start putting the dots or the valence electrons around the atoms, we need to find a home, find the proper place for all valence electrons, all 26 valence electrons. Now, something I'll point out here that I'll mention later, if there happens to be a charge on the molecule, like a plus or minus charge, that means you need to make an adjustment to the total number of valence electrons. Now, if you remember, if a molecule has a plus charge, that means that an electron has been removed from that molecule, okay? Which would mean we'd have to subtract one of the valence electrons. Similarly, if the molecule has an overall negative charge, that means that an electron has been added to it. So in that case, you would need to account for that in your total valence electrons. So that would be 27 valence electrons if this particular compound had a negative charge. All right, step 2. After you count valence electrons, you need to determine which of the atoms is central, the one in the middle. And the vast majority of the time, the central atom will be listed first. Not always, but the vast majority of the time. But the overall rule for that is that the less electronegative atom is the one that's central. All right, so once you have the central atom determined, then you draw single bonds to all of the other atoms involved in the structure. Keep a running count of the valence electrons that you've placed. Remember that every single bond contains 2 electrons. So at this point, we have placed 2, 4, 6 electrons. Onward to step 3. Then give the outer atoms, okay, that means all the atoms except for the central one, an octet. So add enough dots so that each of these outer have a total of 8 electrons around them, a full outer shell. And so at this point, since we have just made 3 octets, we have 3 times 8, or 24 valence electrons we've placed. Remember that we have to place 26, so we have 2 more electrons we've got to figure out where to put. Which brings us to step 4. Any leftover electrons after you've given the outer atoms an octet go on the central atom, which is good because you may have noticed in step 3 that phosphorus didn't yet have an octet of electrons, but it does now. So we've used up all 26 valence electrons. Each of the atoms involved in this structure has an octet, and we are done. It's a stable Lewis structure. That's a very simple, straightforward one. As you're probably not surprised, they're not all that straightforward. Step 5 is really important because when you finish step 4, you will not always have a stable Lewis structure. So let's look at this example. Just quickly, the amount of valence electrons we're dealing with in this sample is 10 valence electrons. At this point, at step 4, if we would go through the steps, we've used all 10 already. 2, 4, 6, 8, 10. Sorry about that. All right, so is this a stable Lewis structure? I'm hoping that you can look at it and see right away. No, it's not. Carbon does not have an octet. It's not stable. So step 5 is really important. You will see this situation a lot. If you run out of electrons before the central atom has an octet, as we have done here, you begin to form multiple bonds. So that means double bonds and or triple bonds with the central atom until it has an octet of electrons. How do we do that? Well, you're simply going to take non-bonding pairs, lone pairs, on one of the terminal atoms and use those 2 electrons to make a multiple bond between that atom and the central atom. Okay, so you can see now that if we have a double bond between carbon and nitrogen, carbon then has 2, 4, 6 valence, not quite at an octet, we're better off. So we need to do it again. You keep making these multiple bonds until the central atom has 8 valence electrons. So we're going to take another of the non-bonding pairs and make a third bond between carbon and nitrogen. That brings us to this structure. And we've still used the right number of electrons. We have a total of 26 electrons, not 26, I'm sorry, 10 electrons that we've placed, but every atom has a full outer shell. Hydrogen, of course, has a full outer shell with only 2 electrons. All right, so here is just kind of an overview of the steps that we went over, just to have them all in one place. Oxygen, 1, I did not. There are some situations in which you will be able to come up with more than one Lewis structure that meets the requirements, that uses the right number of electrons, all of the atoms have a full outer shell, and you've got to choose between 2 or more different Lewis charges. What do we do then? Well, chemists have essentially invented what we call a formal charge to be able to distinguish between the more stable Lewis structure. Formal charge, I want to emphasize, first of all, is they're not real charges, okay? It's really kind of a bookkeeping method to help us see where the electrons are spending more of their time. But I'm going to show you how to determine formal charge. But the bottom line is, what you really need to remember is the formal charge on a molecule should be minimized. The less atoms that have a formal charge and the less overall total the formal charge is, the more stable the molecule is. When I say minimize, the ideal situation is a formal charge of 0. So that plus. All right, so the method that textbooks and online sites show you for determining formal charge is a formula, which is fine if that helps you and you're comfortable. I find it a bit confusing, so I teach it a little bit of a different way. All right, let's look at the Lewis dot structure, or 2 possible Lewis structures for carbon dioxide. If you went through step 1 through 5 earlier in this PowerPoint, you could come up with either one of these structures, and they both look adequate. So how do we determine which one is favored? We're going to assign a formal charge to every single atom in this molecule for each structure, and the one that has the least formal charges will win, be more stable. So what I do to determine formal charge is I use the following. I start with the number of valence electrons that the atom has when it's by itself. Okay, the number of valence electrons an atom has by itself when it's not in a compound. Okay, so let's go ahead and do that for oxygen. Oxygen is in group 6A, right? So it has 6 valence electrons when it's all by itself, right? Yeah. All right, and then we're going to subtract from that the number of valence electrons that belong to that atom in the molecule. The number of valence electrons that belong, and that's the key word. See, that belong to that atom in the molecule. All right, so what do I mean by that? Well, for example, let's look at oxygen again. Clearly, all the non-bonding pairs belong solely to oxygen, right? So it's got 4 electrons that belong clearly to it. Now, when you come to a bond, the electrons in a bond obviously are shared between 2 atoms. So only half of those electrons in a bond belong to each atom. So specifically, what I mean is the double bond between carbon and oxygen contains 4 electrons. 2 of those 4 electrons belong to the oxygen, and 2 of those 4 electrons belong to the carbon. And so that brings us to oxygen. How many electrons belong to it in this structure? 1, 2, 3, 4, 5, 6. Okay, so in this structure, oxygen has a 0 formal charge. That's good. It's a good thing. Let's look at carbon. We know carbon's in group 4A, so it on its own has 4 valence electrons. In this particular structure, carbon also has 4 valence electrons that belong to it. 1, 2, 3, 4. So carbon also has 0 formal charge. All right, so this structure seems very appealing because there are no formal charges. Let's look now at the other potential structure, Lewis structure for carbon dioxide. Again, oxygen is in group 6A. So on its own, it starts with 6 valence electrons. Let's count the valence electrons this oxygen has in this molecule that belong to it. 1, 2, 3, 4. I apologize for the heavy breathing. That's my dog. 5, 6, and 1 of these 2 in this bond. So in this structure, oxygen has 7 valence electrons that belong to it. So it has a formal charge of -1. Going through the similar thing with the carbon. Carbon, we know when it's on its own, has 4 valence electrons. And then in this structure, it has 1, 2, 3, 4 valence electrons that belong to it. So that's good. That carbon in this structure also has a formal charge of 0. This oxygen on the end, as all oxygens on their own, start with 6 valence electrons. In this structure, 1, 2, 3, 4, 5 valence electrons. So in this structure, that oxygen has a formal charge of +1. So the Lewis structure on the left is more stable because it has fewer formal charges. And so we can cross that one out. So that's the process you go by when you have multiple Lewis structures that all seem acceptable. And there is the official formula for calculating formal charge, if that helps you or works for you. All right, so I'm going to work through a little bit more complex specific example for you. This would be a typical question you might be asked on a test. Draw the most stable Lewis structure for sulfur dioxide and assign formal charges to all atoms. All right, so make yourself go through those 5 steps. If I were you, I would turn off the video now and try to see if I could figure this out on my own. Just kind of challenge yourself. So step 1 says count all valence electrons. And so when we do that, we see that there are 18. The central atom, the less electronegative atom, is in fact sulfur, so that goes in the middle. And I'm going to make single bonds to each of the other oxygen atoms. Step 3 says to give the outer atoms an octet, which I've done here. How many electrons have I used at this point? 8 plus 8, I've used 16 electrons so far. So I have 2 left over from the original 18 that I need to put on the central atom according to step 4. All right, so don't stop. It's so common for students to go, okay, I'm done. No, don't forget step 5. Ask yourself, do all of the atoms have an octet? Well, as a matter of fact, no, they don't. Sulfur only has 2, 4, 6 electrons around it, does not have an octet, so that is not stable. Do you remember what we do if the central atom does not have an octet? Then we start making multiple bonds. So it doesn't matter which oxygen you use the lone pair from, but we're going to take off this one, and we're going to use the 2 electrons that were there in that lone pair to draw a double bond. And so now, does sulfur have an octet? Well, let's see. 1, 2, 3, 4, 5, 6, 7, 8. It sure does. That is stable. So you might think you are done, but of course I'm going to take you to yet another level. This is actually not the most stable Lewis structure for sulfur dioxide. So this is getting to a higher level, but I'm going to go to the next page and explain why. If you remember the exceptions to the octet rule at the beginning of the PowerPoint, I said that all elements in periods 3 down through period 7 on the periodic table are capable of expanding their octet. That means they, instead of just 8 valence electrons, they can hold 10, 12, and sometimes 14. And so when you finish with step 5, you need to get in the habit of asking yourself, is this central atom capable of expanding its octet? Do I need to mess with that? Do I need to look at it? Well, yes, as a matter of fact, sulfur's in period 3. It can expand its octet. And just to let you know, it frequently does, very frequently. Sulfur and phosphorus are used all the time as examples for expanding their octet. So what do we mean by expanding octet? Well, it's basically making more multiple bonds, and by doing so, you can potentially not only expand the octet, but potentially minimize formal charges further. So let's look at what I'm talking about. Here's the structure we've got so far. So if I were to calculate the formal charge on all of the, you can leave this out. I found that confuses my students. Okay, if I were to calculate the formal charge in each of the individual atoms, I would find that this oxygen has 0 formal charge. This sulfur has +1, and this oxygen has -1, okay? So there are formal charges in that structure that we were so proud of, that we thought was stable. And now let's expand the octet of sulfur and see if that minimizes these formal charges. So what I'm going to do to expand the octet, same thing I did to make multiple bonds, I'm going to take one of the lone pairs on oxygen, and I am going to use it to make another multiple bond. So I'm going to take that away, and I'm going to put this here. And you can see this is what we get on the left. So now we've got to recalculate formal charge. And let's see, in this case, the oxygen has 0 formal charge. The sulfur has 0, and this oxygen has 0. We have minimized formal charge by expanding the octet of sulfur. How many electrons does sulfur have around it now? 2, 4, 6, 8, 10. Okay? But no formal charges at all. So this original Lewis structure goes away, and this expanded octet version is more stable. And as a matter of fact, the accepted Lewis structure for sulfur dioxide. All right, so we've gone through Lewis structures in quite a bit of detail and all the exceptions. It's really important that you get a practice worksheet and practice it quite a bit for all the different variations. It turns out that when you have more than one Lewis structure for the same compound, we call the relationship between those different Lewis structures resonance structures. And we show the reader resonance structures with a single arrow, single double-headed arrow. So when you see that, that means that these are resonance structures. And I want you to understand the definition of a resonance structure. The only difference between resonance structures is the distribution of valence electrons. That's it. Okay, the ordering of the atoms is the same. But it's simply where you have placed those valence electrons. So again, the best Lewis structure is, we've learned already, is the one that minimizes formal charge. But there's some cases, this is like really kind of upper level now, where you will actually have 2 Lewis structures that have similar formal charges. So look at these 3 resonance structures for this compound. It turns out that the one on the left has more formal charges, a larger value, so we're going to eliminate it immediately. But how do we decide between the 2 on the right? Formal charges are the same or comparable. They all have an octet. What do we do? Well, this won't happen that often, but the key difference here is that the -1 formal charge in one structure is over nitrogen and over oxygen in the other structure. And I bet you can probably guess which of these two is more favorable. Where would a negative charge be more stable, on oxygen or nitrogen? Well, if you remember your electronegativity trend on the periodic table, it goes kind of like this, with fluorine being the most electronegative. And so basically, any atom that's closer to fluorine is going to be more electronegative, which means it has a stronger attraction for electrons. So oxygen is more electronegative than nitrogen, and so it can accommodate or stabilize the negative charge better than nitrogen. So this structure wins. All right, you will have some resonance structures that we call equivalent. They are literally identical. So, for example, if you look at ozone, O3, this heavy breathing of this dog is driving me nuts. Okay, so if you look at O3, and that's formed from oxygen in our upper atmosphere, you have two entirely equivalent resonance structures, and that's just moving the double bond between the two oxygens from one side to the other. And so these are equivalent resonance structures, so I want you to understand what they represent. So they do not go back and forth between one structure and another. This double bond is not bouncing back and forth. Rather, think of the overall Lewis structure for ozone as an average of the equivalent resonance structures, or hybrid, kind of means the same thing. So it's just kind of merging these two equivalent structures. And so think of each of these oxygen-oxygen bonds as containing half of a double bond, okay? So what we say then that each oxygen-oxygen bond in this structure has a bond order. That just says how many bonds does it have. It has a bond order of 1.5. So if it was an oxygen-oxygen double bond, the bond order would be 2. Okay? If it was an oxygen-oxygen single bond, the bond order would be 1. Okay, so since this is the hybrid, we only have one double bond and it's shared between two sites. The bond order is 1.5. Alrighty, just one more exception that's not that common, but just in case you see it. Every now and then you come up with an odd number of electrons to place, and so you end up with a singlet electron. Okay, so nitrogen monoxide is this case. Which of these resonance structures do you think is more stable? Which of these atoms do you think is more stable holding? Well, think about it. They have less than an octet. They only have 7 valence electrons around them. So they would prefer to have 8. So nitrogen or oxygen, which one do you think is more comfortable being down by 1 electron? It turns out, again, down to electronegativity. So you may just write a note to yourself that when you're trying to decide between two Lewis structures that look at electronegativity, if there are formal charges or unpaired electrons. So oxygen, because oxygen's more electronegative, it has a stronger attraction for electrons. So basically, oxygen's going to make sure that it has an octet of electrons, and it's going to have a stronger drive than nitrogen. All right, so the left structure is more stable. I mentioned this in the beginning of this lecture, but I just want to give you an example. Remember there are some elements that are stable with less than 8 valence, the two most common being beryllium and boron. So here's an example of a boron structure that's very stable. Boron trifluoride. If you were to go through the steps for drawing a Lewis structure, and you did not remember that boron is stable with only 6 valence electrons, you might get to this point in drawing your Lewis structure. Those are supposed to be dots, by the way. They're sloppy dots. Okay, and at this point you would have used up all your valence electrons. But again, it's important to remember that boron is stable with only 6 valence If you didn't remember that, you might try making a multiple bond as we've done here. I'm going to show you why that's not a good idea. Okay, so if you make a multiple bond with boron in this structure, look what you've done to fluorine. You've put a formal charge of -1 on one of the fluorine atoms and a formal charge of, +1 on fluorine, a formal charge of -1 on the boron. Now I want you to think of the electronegativities of fluorine and boron. Fluorine is the most electronegative atom on the entire periodic table. You will never see fluorine with any type of formal charge or regular charge of +1. It's just way too electronegative. So that alone is enough to eliminate this structure. But on top of that, boron has a very low electronegativity. It doesn't have a strong attraction at all for electrons. So giving it a formal charge of -1 doesn't seem to make much sense either. So that's out. All right, last slide in this lecture. I want to show you one example that might present challenge to you, just to work through another example. Let's say that you were asked to draw the Lewis structure for the phosphate ion, polyatomic ion. So I'm just going to walk you through that kind of quickly and show you different resonance structures. So phosphorus has 5 valence electrons. Each oxygen has 6 valence electrons. Then we need to remember to add 3 additional electrons for the -3 charge. So that is a total of 32 valence electrons. So you start out with this structure, right? You put phosphorus in the center, draw single bonds to all the oxygens, give all the oxygens an octet, and at this point we have used all 32 valence electrons. So you might originally look at this structure and say, okay, looks good to me, everything has an octet. But remember the question you need to ask yourself. When you finish step 5, you need to say, can the central atom expand its octet? Well, yes, as a matter of fact. Phosphorus is in period 3. It can expand it's in period, it is in period, no, it's in period 4. So it can expand its octet. So let's do that. So we're going to take any of the oxygens, doesn't matter, they're all equivalent at this point. Use one of the non-bonding pairs on oxygen to make a multiple bond. Okay. And you can see now, if you recalculate formal charges, we have now given the phosphorus now as a formal charge of 0, as does this oxygen. And so that's good. That's a good thing. We've minimized formal charge. And I've had students ask me before, well, how do I know when to stop? I mean, can I expand it again? Well, if you're not sure, like usually if the central atom has formal charge of 0, you need to stop. But I'm just going to show you what happens if you didn't know that and you went ahead and tried it again. So let's go ahead and make another one and see what happens. By the way, these are all resonance structures. Okay, we know that so far this one is favored. But let's pretend like we expanded the octet again. Let's see what we would get. All right, so I'm going to calculate formal charges for all of these atoms to see if it was worthwhile expanding phosphorus's octet a second time. So this top oxygen we haven't touched, it's still -1, as is the bottom one. And each of the oxygens have a formal charge of 0 now. And the phosphorus, let's see, phosphorus starts out with 5 when it's on its own. And how many does it have here? 1, 2, 3, 4, 5, 6. So phosphorus now has a -1 formal charge. So you might look at these two resonance structures and say, well, okay, each of them have 3 Formal charges of -1, so aren't they equivalent? No, because the -1 formal charge is on different atoms. On the structure on the left, the formal charges are all on oxygens, and the structure on the right, the formal charges are on the 2 oxygens and also on the phosphorus. So the difference is, would you rather have one of the formal charges on oxygen or on phosphorus? Well, oxygen's more electronegative, so it wins. So but it's pretty safe to just say if the central atom has a formal charge of 0, just stop. That is it for Lewis dot structures for molecules.